What we find out in 7.4 and 7.5 is that they're the same thing. They're the same section. Some textbooks will put them all in the same section, but 7.5 is a series of trigonometric equations where the first thing you have to do is use your identities to substitute so that you can actually navigate through and maybe use some of the tools that we're going to use here, like factoring or solving multi-step equations or something like that. Okay, we can get pretty complex with some of these equations. We can use some complex identities and that kind of stuff. So we'll just see, kind of how we take to this and determine how far we go with the complexity of some of these things. An equation that contains trigonometric functions is called a trigonometric equation, obviously. Those down there, sine squared theta plus cosine squared theta equals 1. That's a trigonometric equation. We know it's an identity, okay, but it is also an equation, okay? If I were to graph the left-hand side and graph the right-hand side, okay, where they cross, where they intersect would be the solutions for theta, right? Now, if that's an identity, we've talked about an identity is always true regardless of your input, right? So when I graph those two things, when I graph sine squared theta plus cosine squared theta, maybe in y1 on my calculator, and in y2 I graph 1, where are they going to overlap? They overlap everywhere, right? Okay, because theta, the input value in an identity does not matter at all. Okay, you're always going to get a true statement. So what I'm trying to say here with that one is, I think it warrants a little bit of discussion. So if we type in, now I have to use, on all your graphing tools, guys, you're going to use x instead of theta. Whatever variable they put in, replace it with x to actually graph. But that's sine squared x plus cosine squared x. Is that the same thing as y equals 1? Yeah. Okay. Where do they overlap? Where do they intersect? Everywhere, right? Every single x value that we can come across is a true statement for that equation. Okay, and that's when that happens, when you get two lines, there are two curves that coincide all the time, you have your identity. Okay, or we label that type of equation as an identity. Computer is being slow, so let's see here. All right. Like 2 sine theta minus 1 equals 0. Okay, we could again take the left-hand side, 2 sine theta minus 1, 2 sine x now minus 1, and then y equals 0. Okay, and we'd be asking where
does the green curve and the red curve cross? Okay. What are the essentially what are the x values of that point there, that point there, that point there, that point there, and what do we recognize with these graphs? How many solutions would I have there? I'm going to have an infinite number of solutions. Okay, so obviously it's not feasible to write every one of them down, so we'll come up with some formulas that actually produce those infinite solutions. Using Desmos, guys, is actually a useful thing here. Now, in regards to using Desmos, if you don't, let me preface it, if you don't have the supporting work, I'm not going to give you credit, but if I type in 2 sine of x minus 1 and y equals 0, and I go through and I just click on that curve and that curve, you see these dots, right? What's really nice about that? Gives me all my answers, doesn't it? And they're in terms of radians, they're in terms of pi, yeah. That's a nice thing, okay? That's a tool to use to check yourself, okay? Now, if I say y equals maybe 1, let's see if it does that. So see these intersections, 5 over 2, 5, 5, 2. It will always, I don't think, give me, see that one doesn't give me it in terms of radians, and we'll talk about what that means to us then, or I guess in terms of pi, what that means to us and how we would kind of deal with that. Does that make sense? Okay, but for the most part, these are going to have, our solutions are going to be in terms of pi. You can use Desmos there to kind of get you verification that you've done things correctly. And then, you know, tangent 2 theta minus 1 equals 0. Okay, another trigonometric equation. This is, remember, that's an identity. This thing here is a what we call a conditional equation. Okay, because it's only true on the condition. Okay, going back to this, it is only true on the condition that x is that value right there where my cursor is, or x is that value there, or x is that value there. Does that kind of make sense? Okay, so that's a conditional equation. Okay, so try to show you how to solve some of these pretty easy. This is an equation, but it's you know, there's a lot of stuff already done for us. If I were to take you know, we'll start down here, I guess, with this example 1 right there, because if I take 2 sine theta minus 1, when we're solving trigonometric equations, we're going to try to solve for the trigonometric ratio, okay, or function. So I'm going to try to solve for sine of theta. So if I'm trying to isolate that thing, what do I need to do first, algebraically? Add 1 to both sides. So I get 2 sine of theta is equal to 1, right? And now 2 is a coefficient for that trig function. So how do I get rid of that 2? Divide. So we get sine of theta is equal to 1/2. So this is an equation, but it probably, for you guys, when you start dealing with these questions, it's going to first be presented kind of like that. And you got to do a little bit of preliminary work. I showed the last class that, you know, some people don't like you know, a word in their equation, okay? So if you do this, can I then say 2u minus 1 is equal to 0? 2u is equal to 1, u is equal to 1/2. But what was u? We said it was sine theta. Does that get me the same thing right there? Okay, so you can do that. That's actually a tactic that we'll use in some more difficult questions here down the road. But when we solve this and we get sine of theta is equal to 1/2, our question is, you know, our variable is theta. We're trying to figure out what are the values of theta that this is true for. Okay? Well, going through my unit circle, the idea is if I'm going through my unit circle, what values of theta, or what radians or degrees do you get the sine to be 1/2? One of them is at 30 or pi over 6, right? And I keep going around, and then 5 pi over 6. Keep going around, and those are the only ones, right? So my solution to this equation, the solution to, 2 sine of theta minus 1 equals 0, is when theta is equal to pi over 6 or 5 pi over 6. Because if you put pi over 6 right here for theta, what's sine of pi over 6? You get 2. Sine of pi over 6 is 1/2, right? Minus 1. Is that a true statement? Does 2 times 1/2 minus 1 equal 0? Yes. Okay. And then if you do it for 5 pi over 6, you get the same. Yes. Okay. You satisfy the equation. Now, those solutions, let's think about those. Those solutions were within one period. Because how many times did I kind of walk myself around the circle here? Once. Okay? So these solutions for theta are right now between the interval 0 to 2 pi. Okay? If you look down here, it says find all the solutions. Okay? Because I could put something else in here that is bigger than pi over 6 and bigger than 5 pi over 6 that still works. Okay? Think about this. Maybe if I'm in degrees, can I, there is my first one of 30 degrees, right? If I go around one more complete time, that's 390 degrees, isn't it? Which would be, pi over 6 plus 2 pi, correct? Does that make sense? Okay. Or was that 13 pi over 6? Okay. Trying to prove that maybe with this. If I go 2 sine of 13 pi divided by 6, it gives me 1, right? Okay. Does 1 minus 1 give me 0? Because that was the equation. 2 sine of x minus 1 equals 0. And we do have 0. So 13 pi over 6 satisfies the equation, right? And the idea, guys, is when I'm asked for the infinite number of solutions, it's, all those times that, all those coterminal angles with 30. Okay? So 750 would work. 1,110 would work. Okay? We'll find out that, what's that one? 2,900 and, can't get to it. I think it's 2,910 would work, okay? So everything that's coterminal with pi over 6 or 30 is going to be a solution. Speaking of that graphically, if I'm just going to do this real quick. Let's see how x equals a. Create slider. I got y equals sine of a. And then I want all right, what I just created, we actually call that a parametric equation. You don't need to write that down or know that right now, but it's an equation that is based off ultimately a third variable. Okay, so this line here is based off of a third variable a. This line here is based off a third variable a. But it provides, their intersection provides me that point, right? If I start to move a, you see that point, it's moving up and down, right? And it's moving up and down like the sine function does. If I were to trace that point. So that's the sine function. Okay. I want, so I'm going to hide those. And I also want to create another point, B. And I want B to actually have the same x coordinate as A. All right, so I'm just going to say x coordinate of A. And I want its y coordinate to be 1/2. Okay. So what this is going to allow me to do, guys, is kind of show you that when we move these values, okay, it didn't trace the way I want it to. Hold on. Trace. Okay. Would you agree that about right there, those two things are equal? That's the intersection of 1/2 and sine, right? Okay. Keep going. Would you say at about right there, they're equal again? Okay. Now I don't have it out too. I'll scroll out here. Yep, I figured that would happen. So right there, they were equal. There, they became equal again. When I get out to 2 pi, let me change the axes here. I had this in the last class, set it before class, but I've messed it up. Or I deleted it. We get out to 2 pi, and they don't intersect anymore, right? So we're seeing bear with me. Trying to get the x-axis to let's do it this way. Pi over 2. Go basic. Let's go. That's fine. Let's go 4 pi. All right, good enough. As I start moving those points, okay, we start to see that they were the same here. They were equal about right there, right? They're equal about right there, okay? And that point there, we said was pi over 6 from the unit circle. That point is 5 pi over 6 from the unit circle, okay? Now, this point over here, where they end up intersecting again right there, or right here, okay, let's look at this first one here. This one there, okay, is analogous to that one there. Does that make sense? But it's just in the second period of the curve. Is that all right with everybody? If I put the full curve in here instead of these traced out points, I go sine of x, okay? And let's put y equals 1/2 in as well, okay? That point right there is the intersection of those two things in the first cycle, 0 to 2 pi. That point right there is that first intersection in the cycle from 2 pi to 4 pi. So these 2 points I have arrows on, they are related to one another, okay? If I look at just the intersections here, let's just take that point there of C and that point there of D. And I ask this thing to take the x value of C and the x value of D. I'm going to subtract them in that order. You see that it gives me back 2 pi. So there's a distance of 2 pi between those. Does that make sense? What is going to be the distance between D and E? 2 pi. Is E another solution? Yeah. What's going to be the distance between E and F? 2 pi. Okay, so let me zoom out a little bit so I can write all this down. We know that point right there is located at pi over 6, right? That point right there, you just told me from pi over 6, we just used C and D's x values and subtracted them and found that distance right there to be 2 pi, right? So wouldn't this point right here be pi over 6, starting at 0, it'd be pi over 6 would get me there, and then plus 2 pi would get me to D. And now how far do I have to go from D to get to E? 2 pi. So D is my starting point now, so pi over 6 plus 2 pi. That's D. Add 2 pi to it, and I get E. What I'm going to add to that to get to F. Okay? So this is the kind of the rectangular coordinate concept of revolving around my unit circle multiple times. Does that make sense? Okay. Let's think about this. How many 2 pi's do I add here? 0. So this is 0 times 2 pi. How many here? 1. How many here? 2. How many here? 3. If I want to find this one right here, point G, how many would you think I add? 4. What if I wanted to find the one right there? Yeah, that's going to be pi over 6 plus negative 1 times 2 pi. The next one would be negative 2, right? What's negative 2, negative 1, 0, 1, 2, 3? What kind of numbers are those? If I have negative infinity up to negative 3, negative 2, negative 1, 0, 1, 2, 3, all the way up to positive infinity, what did we call that set of numbers? Those are your integers, right? Anybody remember? Did somebody say that? Okay. Say it with some conviction. Okay. The integers are defined using the letter Z. Okay. And it's that kind of bold looking Z. Does that make sense? Okay. Now, the reason I'm saying this is because I want to be able to show the infinite solutions. So pi over 6 is one solution. Okay. But I don't want to write 13 pi over 6 and then 25 pi over 6 and write all my infinite solutions because I'll die doing that, right? Okay. So how can I encapsulate all those infinite solutions? I write plus whatever the period is for sine, because that's how we're seeing these replicate here. So I'm going to write 2 pi, and then we'll multiply it by some value k, where k is an element of our integers. Or k is an integer. K is 0, 1, 2, 3, 4. So if k is 2, it's going to give me that point E. Does that make sense? If k was 3, it's going to give me point F. If k was negative 2, it'll give me that second point over there on the left-hand side of the y-axis. Okay? Does that make sense, everybody? So that is the formula that we write for expressing infinite solutions. Okay? And you might want to write it this way, or write a sentence here, that in finding, to find, or maybe express infinite solutions, you're going to take your initial solutions inside the initial period, okay, and then add the period times K, where K is an element of your integers. Okay. Now I write it that way because of what we're going to do in the next couple of days when the periods change. Okay. Maybe we'll find sine of 2 theta is equal to 1/2 instead of sine of theta equals 1/2, and we can address that without using AB identities, but then the period changes. Initially, right now, you just got to know that your period for sine is what? 2 pi. Your period for cosine is 2 pi. Your period for tangent is pi. Okay. So let's do one for tangent real quick, and we'll kind of stop there for today. If I look at or part B here, it says find tangent squared theta minus 3. Okay. I think we have the ability, tangent of theta is my kind of variable term here. Is tangent squared theta mean the same thing as tangent theta squared? Minus 3 is equal to 0, right? Let's try to isolate tangent theta. What would I do to both sides if I'm trying to isolate that? Add 3. So tangent theta squared is equal to 3. And now do what? Okay, so I'm going to take tangent theta. I'll square that side. And now I got to square the right-hand side, right? But when you square root 3, what do you get? You get plus or minus, okay? So here we have to have both solutions. Now, you guys might not be 100% sure on where radical 3 shows up in your unit circle. This is radical 3 over 2 comma 1/2, right? This is 1/2 radical 3 over 2, and this is, again, pi over 6, and this is pi over 3. If I divide these, sine divided by cosine, this is the one that produces radical 3. Is that okay? So theta then is pi over 3. And that's when the square root is positive root 3. Right there, is that going to be negative 1/2 divided by radical 3 over 2? Sorry, radical 3 over 2 divided by negative 1, sine divided by cosine? Is that going to be radical 3 again? But it's now going to be the negative radical 3, right? Does anybody remember what that point right there on the unit circle, that is a y-axis reflection of that point? 2 pi over 3. Okay. You're also going to get this point down here to have the same coordinates. Does anybody remember what the x-axis reflection of that point is down here? Four pi over 3. And then you're going to have one right here as well. Any guesses? 5 pi over 3. Okay. You're going to see that one of the fundamental things for doing these problems is to know your unit circles. So some of us are going to have to brush up on that again. Okay. Those are the solutions inside one period. Okay. If we look at that graph, okay, tangent squared x minus 3, where does that equal y equals 0? Okay, it would be at, we said, what, pi over 3, comma 0 is that point. 2 pi over 3, comma 0 is that point. 4 pi over 3, comma 0 is that point. And 5 pi over 3, comma 0 is that point. Is that the solutions around the unit circle? Okay. Now, how do I find these other ones? A is going to correlate to that point right there, correct? Okay. And actually, sorry. A is not going to. So if I take A plus, I don't know if this is going to work. We'll pick up with this tomorrow.